Here is a secret about the bleeding edge of AI right now. Sometimes the smartest, most advanced artificial intelligence in the world acts exactly like a broken robot vacuum cleaner.
It really does, yeah. It's
Yeah,
kind of funny to watch.
it is. And you have probably seen the headlines about these massive strides in autonomous systems, right?
Yeah.
But when you actually look under the hood at what happens during long, complex tasks, well, these brilliant models can get entirely stuck in a corner. They just bump into the same chair leg over and over again.
Completely paralyzed by their own logic.
Exactly. I'm your host, by the way, and welcome to today's Deep Dive.
And I'm your resident expert, really excited to dig into this one.
So today we are exploring a really fascinating state-of-the-art foundational paper. It's titled No Time Like the Present, Agentic Test-Time Training for LLM Agents.
Catchy title, I know.
Right. And our mission for this deep dive is to understand a major roadblock in AI development. We want to know why smart AI agents suddenly get, well, stuck when doing long tasks, and look at the ingenious new method developers using to fix it.
Because we are moving way beyond standard prompts here, you know? The whole industry is shifting toward agents that execute these long multi-step goals.
Okay, let's unpack this. Because that shift from a chatbot to an agent is a huge leap.
It's massive. That shift to agentic environments is fundamentally changing how we evaluate these models. We aren't just looking at an isolated question and answer exchange anymore.
Right, it's not just, hey, write me a poem.
Exactly. We are dropping an AI into a simulated household or a massive software engineering workspace and asking it to navigate. It has to take an action, observe the consequence of that action in the environment, reason about what to do next, and then take another action.
It's a continuous rollout of decisions.
Yeah, a continuous rollout. And the roadblock this paper tackles is the severe degradation that happens during those long task rollouts. As the simulation runs on, the models start revisiting places they've already searched. They repeat actions that just failed.
Just totally spinning their wheels.
Right, and they completely abandon the logical strategies they were using perfectly just, 10 steps prior.
To really grasp the solution, we first have to witness the problem in action. And the researchers highlight a great case study from a benchmark called ALF World, which is a text-based simulated household environment.
Yeah, it's a classic testing ground.
And they zero in on game 100, which is infamous as the soap bar task. The agent is given a really straightforward objective. It just has to find 2 bars of soap and put them in a garbage can.
Seems simple enough.
Right. And for the first 8 steps, the AI is brilliant. It explores the cabinets. It locates soap bar 1. It finds soap bar 4 resting on a countertop. It is perfectly executing a logical search pattern.
But then we hit step 9.
Right. At step 9, the logic just evaporates. The agent has soap bar 1 in its hand, and instead of carrying it to the garbage can, it puts the soap bar back on the counter.
It actively reverses its own progress.
Yeah. Then at step 10, it picks up soap bar 4. Step 11, it puts soap bar 4 back on the counter. And from there, it just gets locked in. Pick up the soap, put down the soap, pick up the soap, put down the soap.
The dreaded infinite loop.
Exactly. It repeats this exact useless loop 41 times until it hits its 50-step budget and just fails the whole simulation. Like I said earlier, it's the Roomba trapped in the corner.
Yeah, and if we connect this to the bigger picture, taking that Roomba analogy a step further, if a robot vacuum is trapped against a chair leg, it doesn't mean the vacuum has forgotten how to suck up dirt, right?
Right, the motor isn't broken.
Exactly. The competence is still there. And this is what makes the AI failure so fascinating. The underlying weights of the neural network still contain the knowledge of how to complete this household chore.
So it has the potential.
It has the potential, yeah. But it suffers from a phenomenon the authors call within episode drift. Over a long task rollout, the model's focus basically drifts away from the useful evidence it gathered early on.
Like it loses its train of thought.
Precisely. It loses its grip on its own promising strategy, even though it retains the raw capability to actually succeed.
So my natural instinct is to wonder, why can't we patch this with the tools we already use? We have optimization techniques designed to keep AI on track.
We do, but they really fall short for this specific kind of multi-turn drift. Take reflection, for example.
Oh, right, where it reflects on its mistakes.
Yeah. You wait for the agent to fail the task, and then you have it reflect to revise its prompt for the next attempt. But the problem is, that happens across separate trials. It's a post-mortem analysis.
So it leaves the agent completely unguided during the actual live simulation run.
Exactly. It's like giving a post-game locker room speech when you actually need a coach calling audibles on the field before the clock runs out.
Okay, that makes sense. But what about longer context windows? I hear about those all the time. Just give it more memory.
Engineers definitely try that route. The idea is to just feed the entire running history of the simulation into the model's memory, but deep learning research consistently shows that large language models get lost in the middle.
Lost in the middle.
Yeah, as the context grows to tens of thousands of tokens, the attention mechanisms inside the transformer architecture just start to decay. The model struggles to prioritize earlier evidence, even if it's sitting right there in the prompt.
Huh. Okay, what about static test time training, or static TTT?
So that adapts the model's internal weights based on the specific test input it receives, but it only does this adaptation once to a fixed frozen input right before the task begins.
Oh, so it doesn't adapt to the evolving, messy reality of a 50-step dynamic environment.
Exactly. It's just a one-time adjustment.
Okay, so if static training doesn't work for a dynamic task, and long context windows just overwhelm the attention mechanism, the obvious answer seems to be continuous training.
You'd think so.
Right. Like, why not just let the AI train and update its own neural weights during the task, step by step, as new information comes in? But the paper points out this introduces a dangerous new problem.
A very dangerous one.
And I want to dig into the mechanics of this because, I'll be honest, it feels counterintuitive to me. Wait, isn't learning as you go a good thing? Like, if I'm playing a new video game, I want my brain to continuously update based on what's happening. If I jump into a pit of spikes and my character dies, my brain updates its internal weights, right? Spikes equal bad. Why is that kind of continuous real-time learning destructive for the AI agent?
So the distinction comes down to where the training data is originating. In your video game scenario, the feedback is exogenous.
Exogenous, meaning external.
Right. It comes from outside of you. The game environment has rules, spikes cause damage, and those rules exist independently of your actions. You are learning from an external ground truth.
Okay, I follow that.
But in continuous test time training for an AI agent, the training stream is endogenous. The system is basically generating its own reality.
Endogenous meaning the data is being produced from within the system itself.
Yes. Think about the mechanics of the agent cycle. The AI generates an action, like put the soap on the counter, along with its internal reasoning for doing so. That text output immediately becomes the training data for the next step.
Yeah.
Yeah, the model runs a training step on that self-generated text, updates its neural weights, and then uses those newly updated weights to generate the very next action.
So it's continuously reading the textbook it is currently writing.
That is a perfect way to put it. And that creates a highly sensitive feedback loop with two distinct regimes. When the agent is making progress exploring new rooms, finding new objects, the text it generates is full of fresh, useful evidence.
So in that regime, it's a good thing.
Yes, training on that text helps the model adapt to the new environment. But consider what happens in the second regime when the agent gets stuck.
Oh, no. It starts generating the text, put the soap on the counter, pick up the soap, put the soap on the counter.
Exactly. The update stream is now continuously replaying the exact same failed actions and flawed reasoning patterns. Because the training is endogenous, the AI is literally training itself to be stuck.
It's brainwashing itself.
Basically. By running back propagation on those repetitive, useless commands, it strengthens the specific neural pathways that generate that mistake. It's actively reinforcing the behavior that is preventing progress. The authors call this a repeated self-training loop.
It's mathematically cementing its own failure. The more it bumps into the chair leg, the more its internal weights adjust to believe that bumping into the chair leg is the optimal strategy.
It spirals very quickly, yeah. The researchers tracked the internal metrics during these failed runs, and they observed an early and sustained rise in update text repetition. The model's vocabulary just collapses.
It just regurgitates the same words over and over.
Exactly. It stops considering alternative verbs or objects.
Which means we need a way for the AI to keep the benefits of continuous learning because it still needs to adapt to novel information while filtering out those repetitive stuck loops.
Right. It needs an intervention in that feedback loop.
Well, here's where it gets really interesting. The paper's solution is Agentic Test-Time Training, or aTTT. And the best analogy I could think of for how aTTT approaches this is studying a textbook with a highlighter.
I like that. How so?
Let's say you're reading a chapter and you encounter a paragraph where you already know, like 90% of the concepts. You don't just rip the page out and throw it away. The paper refers to that aggressive approach as sequence filtering, right?
Right, throwing away an entire update block just because it contains some repetitive actions.
Yeah, and if you rip the page out, you lose the 10% of the paragraph that contains a brand new vital fact. So instead, aTTT acts like a smart highlighter. You only highlight the 10% that is novel. When you study, you only burn the newly highlighted information into your long-term memory, and you ignore the repetitive filler.
That visualization captures the goal perfectly. From a mechanical standpoint, aTTT achieves this through a process called token-level reweighting.
Token-level reweighting. Break that down for me.
Well, instead of looking at a whole sentence and deciding whether to keep it or toss it, the algorithm evaluates the training data at the granular level of individual tokens, which are basically pieces of words.
But how does it actually know what to highlight? How does an algorithm detect that a token is repetitive filler versus a novel discovery?
It uses something called n-gram tracking as a diagnostic signal. Specifically, it looks at 3 grams, which are sequences of 3 consecutive tokens.
Okay, so chunks of 3 tokens.
Right. As the agent generates new text for its next update, the system scans that text and cross-references every 3 gram against the history of everything it has already generated in this specific simulation run.
Oh, I see.
Yeah, so if it finds a token that is part of a 3 gram, it has seen repeatedly say the phrase, it flags it.
But wait, I have a major question about this. If the model flags a repeated phrase and dials down the training weight, aren't we risking the AI forgetting its main objective?
How do you mean?
Well, if the prompt says find the garbage can multiple times and the algorithm suppresses repeated words, won't the AI just ignore the word garbage can entirely? Doesn't it need that repetition to remember the goal?
That is a crucial distinction to make, and it really comes down to the difference between the model's reading context and its gradient updates.
Okay, explain that difference.
We are not deleting the words from the text the AI is reading. The prompt still says, find the garbage can. The agent can still see that text in its context window. What aTTT modifies is the loss weight during the training step.
So what exactly is a loss weight in this context?
Think of a loss weight as a volume knob for learning. When a neural network trains, it calculates a gradient, which is basically a mathematical arrow pointing in the direction the weights should adjust to get better at predicting the next word.
Okay, a volume knob.
Right, so if the loss weight is set to 1, the model learns from that token at full volume. It significantly adjusts its internal connections. But when aTTT flags a repetitive token, it dials that loss weight down to a floor of 0.05.
Oh, wow. So barely learning from it at all.
Exactly. It doesn't erase the token from the environment, but it tells the back propagation algorithm, hey, do not adjust the model's internal weights based on this word. We have already learned this pattern.
Oh, I see. So the AI still knows the soap is there, but its underlying behavioral policy stops shifting further toward the act of picking it up and putting it down. It stops burning the rut deeper.
Yes, and this is why token-level reweighting is so powerful compared to just throwing out whole sentences.
Because it can isolate the new stuff.
Exactly. Imagine the agent is stuck in a repetitive loop, but during one of those loops, it happens to notice a new object in the corner of the room. A towel.
Okay.
The repetitive reasoning template around that observation gets its loss weight dialed down to 0.05. But the specific tokens for you see a towel have never appeared in a 3 gram before. They are novel.
So those novel tokens keep a full loss weight of 1.
Precisely. The agent learns the new fact that the towel exists without accidentally reinforcing the stuck behavioral pattern it was executing when it found it.
It preserves the novelty while suppressing the repetition.
Exactly what you'd want a smart filter to do. It stabilizes the training stream, so the model only learns from productive exploration.
Okay, a theoretical mathematical filter is great, but taking this out of the household simulation and looking at the hardware requirements, I mean, this sounds computationally terrifying.
It really does sound heavy, doesn't it?
Updating a massive neural network's weights in real time, every few steps of a simulation, while it's actively trying to solve complex problems. Before we talk about how they pulled it off, let's look at the benchmarks to see if this actually works. They tested this on SWE Benchlight, which is a massive leap from picking up digital soap.
Yeah, SWB Benchlight is a notoriously difficult software engineering benchmark. It doesn't just ask the AI to write a quick Python script.
Right, it's way more involved.
It provides the agent with a real complex GitHub repository and a logged issue. The AI has to navigate multiple directories, read through thousands of lines of code to understand the architecture, pinpoint the bug, and write a patch to resolve it.
Which requires hundreds of sequential steps of reasoning and tool use. It is the perfect breeding ground for within-episode drift.
It really is. The trajectories are incredibly long, and they tested aTTT on the Quinn 3.5 27B model, a highly capable 27 billion parameter open weight model.
A beast of a model.
Yeah. And even on a task this complex, applying aTTT improved the issue resolution rate by 4.9 points.
That's significant.
Very. And on the ALF World Household benchmark, it improved success rates by up to 5.0 points.
Okay, I have to close the loop on our ALF World case study.
Yeah.
What actually happens to our poor agent in Game 100, the one stuck in the 41-step loop of picking up the soap and putting it down?
The researchers provided the exact trajectory of the redeemed run. It's pretty cool. With the TTT running under the hood, the agent explores the kitchen identically for the first 8 steps. It finds the soap.
And at step 9?
At step 9, instead of putting the soap bar back on the counter and triggering the 41-step loop of doom, the agent simply walks to the garbage can.
Because the urge to repeat the counter placement was down-weighted.
Yes. The repetitive action was no longer being reinforced, which allowed the agent's existing knowledge of the actual goal to take priority.
Amazing.
At step 10, it puts the first soap bar in the garbage. It walks back, retrieves the second soap bar, and completes the entire 50-step limit task in just 14 steps.
Wow. The Roomba mapped the chair leg and just drove around it.
Pretty much.
Now, we have to talk about the engineering because I am trying to wrap my head around the server costs of this. If I'm a developer, doing continuous gradient updates for every single AI agent running a task sounds incredibly slow and expensive. How are they deploying this practically without grinding the system to a halt?
Well, they engineered a brilliant asynchronous system architecture. It basically physically decouples the inference, the part where the AI generates the text from the training.
Okay.
To do this, they relied on VLLM, which is a highly optimized open-source serving engine for large language models, and they combined it with something called runtime LoRa.
Oh, LoRa, so low-rank adaptation. I know it's a way to fine-tune models, but how does it work in a live runtime environment?
So normally, fine-tuning a 27 billion parameter model means adjusting all 27 billion weights, which requires massive GPU clusters and days of computation, right?
Right.
LoRa bypasses that. It freezes the massive base model completely, so those weights never change. Instead, it creates a tiny, separate mathematical matrix, the LoRa adapter, that sits alongside the base model.
I see.
During training, only the weights in this tiny adapter are updated. It acts as a lightweight patch that modifies the outputs of the frozen base model.
It's like a temporary lightweight brain attachment that just slightly nudges the main frozen AI's thinking.
That's a helpful way to picture it, yeah. In the aTTT setup, the heavy base model is loaded into the VLLM serving engine, and it acts as a shared resource. But each individual simulation run on each active agent gets its own private, tiny LoRa adapter.
Oh, that's clever.
They set up the system to serve 16 episodes concurrently.
So 16 different agents are running around 16 different environments all at once, sharing one frozen brain.
Yes. And here is where the asynchronous magic happens. While those agents are busy observing their environments and generating their next actions, a separate set of dedicated training GPUs are working in the background.
Oh, they split the workload.
Exactly. When an agent generates new text, that text is shipped over to the training GPUs. The training GPUs apply the token-level reweighting, calculate the gradients, and update that specific agent's tiny LoRa adapter.
But wait, how does that updated adapter get back to the agent without pausing the simulation?
Through the VLLM runtime API. When the background training GPU finishes updating the adapter, it hot swaps the new adapter back into the VLLM serving engine's active memory.
Hot swaps it.
Yeah, and because LoRa adapters are so small, this memory swap happens in under 100 milliseconds.
Under 100 milliseconds. So the agent generating actions doesn't even perceive a delay. It just suddenly has slightly updated intuition for its next step.
Precisely. And update processing for agent number 1 doesn't block the generation for agent number 7.
That is incredibly efficient.
It is. By decoupling the heavy lifting of training from the fast-paced generation, running this concurrent system is 6.6 times faster than trying to do it sequentially.
Wow.
And in terms of overall efficiency, it only costs 1.9 times the wall clock time of a baseline run that has no test time training at all.
That engineering feat is almost as impressive as the mathematical filter itself. I mean, it makes continuous agent learning practically deployable.
Exactly.
So what does this all mean for you? As we move into an era where we rely on AI for long-horizon autonomy, We aren't just asking it to write a haiku. We're asking it to act as a personal assistant, managing a schedule for a week, or asking a coding agent to build and test an entire app architecture from scratch.
The stakes are getting higher.
Right. And in those scenarios, reliability is everything. A model with 99% accuracy is effectively useless if it gets trapped in an infinite logic loop on step 45 out of 100. This research provides a mechanism to ensure the AI doesn't lose its mind halfway through a workday.
And building on that, the authors include a philosophical nuance in their discussion of the results. They emphasize that aTTT does not teach the AI new fundamental abilities from scratch.
It's not going to teach the model how to write Python if it was only trained on English.
Right. It relies purely on the live data from the episode itself. There is no external human supervisor jumping in to provide a hint. Its actual superpower is stabilizing existing competence.
Stabilizing competence, I like that.
Yeah, the researchers noted that the performance gains were heavily concentrated in settings where the model already had a meaningful chance of solving the task, but was simply prone to losing its progress over long trajectories. It's an algorithm designed to prevent an intelligent system from squandering its own potential. It keeps the agent grounded in its own reality as the context grows.
It's basically a localized algorithm for maintaining focus. Well, to recap the journey we've taken through this research, we started by examining the roadblock of within-episode drift, where capable AI agents get trapped in endless loops during long tasks.
And we broke down how the seemingly obvious fix, continuous endogenous training, actually backfires, causing the AI to mathematically reinforce its own mistakes in a repeated self-training loop.
Right. And then we explored the solution, Agentic Test-Time Training. By utilizing 3-gram tracking and token-level loss reweighting, the system acts like a smart highlighter.
Suppressing the repetitive noise by dialing down the gradient updates while preserving the full training weight of novel discoveries.
And through the clever use of asynchronous LoRa hot swapping, they managed to do it all in real time without melting the servers. It's a massive step forward for the reliability of autonomous agents.
It really is.
And, it leaves me with a final thought outside of the code. This entire paper centers on an artificial intelligence requiring a strict mathematical filter to stop obsessing over its own repetitive mistakes.
Right.
Forcing itself to focus only on novel, productive information so it can move forward. It makes you wonder, well, if we were able to track our own human inner monologues, how often are we stuck in our own repeated self-training loops? We ruminate. We replay the same anxieties. We bump into the same emotional chair legs over and over, internally reinforcing our own ruts.
It's a very human problem.
Yeah. What would happen if we could apply our own token-level reweighting to our daily habits? What if we could mentally dial down the lost weight of our repetitive thoughts and highlight only the novel observations that actually move us forward? Thank you for joining us on this deep dive. Keep questioning the systems around you and keep learning. We'll catch you next time. And until then, try not to get stuck in the corner.